It's time for a more sophisticated, yet easy to understand, example. We will look into market segmentation. I'll open a clean Jupyter notebook and import all the relevant packages, including the k-means module. Next, we should load the dataset, located in 3.12, example.csv. In the CSV, we've got data from a retail shop. There are 30 observations. Each observation is a client, and we have a score for their customer satisfaction and brand loyalty. Let's see how the data was gathered. Satisfaction is self-reported. People were basically asked to rate their shopping experience from 1 to 10, where 10 means extremely satisfied. Therefore, satisfaction here is a discrete variable and takes integer values. Brand loyalty, on the other hand, is a tricky metric. There is no widely accepted technique to measure it, but there are different proxies like churn rate, retention rate, or customer lifetime value. In this dataset, loyalty was measured through the number of purchases from that shop for a year and several other factors found to be significant. The range is from around -2 to around 2, as the variable is already standardized. That's something that often occurs, especially when creating latent variables like this one. Okay, let's plot the data. We can kind of identify two clusters by looking at the graph. This one and that one, right? Well, before we perform any analysis, let's reason about the problem for a while. We can divide this graph into 4 squares. Low satisfaction, low loyalty. Low satisfaction, high loyalty. High satisfaction, low loyalty. And high satisfaction, high loyalty. So, going back to our 2-cluster solution, we realize it didn't make much sense, right? What would these 2 clusters represent? The first one looks like low satisfaction, low loyalty, but the other one is all over the place. It seems to me that a 2-cluster solution won't cut it. But enough speculation. Let's leverage the new knowledge we possess and learn something new. First, I'll copy the data into a new variable called x. Next, I'll use the same code we have used so far. K-means equals k-means of 2. K-means dot fit x. Clusters is a duplicate of x, and the column cluster pred of this data frame will contain the cluster where a particular observation was predicted to be placed by the algorithm. Next, I'll quickly plot the data. What we see are 2 clusters, but they aren't the 2 we imagined, are they? If you examine the plot closely, you will realize that there is a cutoff line at the satisfaction value of 6. Everything on the right is one cluster, everything on the left, the other. This solution may make sense to some, but most probably the algorithm only considered satisfaction as a feature. Why? Because we did not standardize the variable. The satisfaction values are much higher than those of loyalty, and k-means more or less disregarded loyalty as a feature. Whenever we cluster on the basis of a single feature, the result will look like this, as if it was cut off by a vertical line. That's one of the ways to spot if something fishy is going on. Okay, satisfaction and loyalty seem equally important features for market segmentation. So, how can we fix this problem? How can we give them equal weight? Yes, by standardizing satisfaction. There are several ways to do that in sklearn. The simplest one I am aware of is through the pre-processing module. So, from sklearn, import pre-processing. Then we will declare a new variable called xScaled equal to preprocessing.scale of x. Scale is a method which scales each variable separately. In other words, each column will be standardized with respect to itself. Exactly what we need. And it's done. As you can see, xScaled is an array which contains the standardized satisfaction and the same values for loyalty. That's because loyalty was already standardized. It had a mean of 0 and a standard deviation of 1, that is. Okay, let's continue in the known way. Since we don't know the number of clusters needed, the elbow method will come in handy. Let's declare a list, WCSS. For I in range from 1 to 10, colons. K-means equals K-means of I. Again, K and M are capital when referring to the method. K-means dot fit X. And we will append the result to the WCSS list using the inertia method. Great! Note that the range is from 1 to 10, so we will get the WCSS for a 1, 2, 3 until 9 cluster solutions. That was an arbitrary decision on my side. Finally, let's plot WCSS versus the number of clusters as we did in the previous lectures. The result is an elbow. Given this graph, think about the correct number of clusters we should use. We will explore the different solutions in the next lesson. Thanks for watching.